Hello and welcome to Learn with Ryan. Today what we're going to look at is differentiation from first principles. So before we dive into that, we need to understand what we mean by differentiation and what we mean by finding the derivative of a function. So when we're finding the derivative of a function, what we're essentially doing is finding the gradient of a particular curve at a particular point. Now, many of you will be familiar with working out the gradient of a straight line. So we've got a straight line here. Now, when it comes to working out the gradient of a straight line, the gradient is the same no matter where you are on that line. For example, if you are here, the gradient or the steepness is the same as if you were here on the line, okay? However, when we are dealing with a curve, the gradient is constantly changing. So for example, I'm going to draw a curve. Okay, so the gradient is not the same throughout the curve. So for example, the gradient here is not as steep as the gradient here. So the gradient at this point is going to be higher than the gradient of this point. And that's what differentiation is all about. It's about finding the gradient at a particular point on a curve. So let's see how we would work out the derivative of a particular function. Now suppose we've got a curve here, so a function represented by this curve. Doesn't matter what the curve is, it's just a random curve just to generalize it to see what's going on. And suppose we've got the point P which lies on that curve. And the idea is to work out the gradient of the curve at the point P. Okay, so what we need to do is we need to think about a chord connecting point P and another point on the curve. Let's call it Q. Okay, so we've got my point P and we've got the point Q and we've got the chord connecting it. Now, if we were to just work out the gradient of that chord, it's not going to give me the exact gradient or at the point P. It's just going to give me an approximation for the gradient. So we need to consider point Q approaching point P so much so that it actually is the point P. So notice that as Q approaches P, the chord connecting P and Q gets smaller and smaller and smaller. But then when point Q is actually the point P, we end up with the gradient at the point P when we consider the gradient of the chord. Suppose I've got my point Q here. And suppose we've got, I don't know if it's a different color. Suppose we've got the chord connecting P and Q. So we'll call the chord PQ. So let's see how we would work out the gradient of that chord. So what we need to do is we need to think about the x coordinates and the y coordinates of P and Q. So suppose this function is called f of x. So I'm just going to call the function y equals f of x. Okay. Now the x coordinate of Q, we're just generalizing it, remember. So it doesn't matter what we call the x coordinate, I'm just going to call it x naught. So that's the x coordinate of Q. And if x naught is the x coordinate of Q, the y coordinate must therefore be f of x naught. Okay, so the y coordinate of Q is going to be f of x naught, because remember the function is f of x. So we've got the x coordinate and the y coordinate of Q. Now let's consider the x coordinate and y coordinate of P. Now let's suppose that to go from the x coordinate of Q to the x coordinate of P, we have moved h units. Okay, so we've moved a particular distance, which I'm going to call h. So if we've moved a distance of h units, the x coordinate of P is therefore going to be x naught plus h. Okay, and therefore if the x coordinate of P is x naught plus h, the y coordinate of P is therefore going to be f of x naught plus h. So now that we've got the x coordinates and the y coordinates of p and q, we can actually work out the gradient of the chord PQ. So gradient of PQ, so remember it's just a straight line we're dealing with, and to find the gradient of a straight line it's the change in y divided by the change in x. So the change in y on top, which is essentially f of x naught plus h minus f of x naught, so f of x naught plus h minus f of x naught, and then we're dividing that by the change in the x's, which is essentially x naught plus h minus x naught. Now notice that on the bottom the x naughts cancel out, so what we are left with on the bottom is just h. So we've got f of x naught plus h minus f of x naught, and that's divided by h. Now that's not the end of our story, unfortunately, because what we've done is we've just worked out the gradient of the chord. But remember what I said, the gradient of the chord is just an approximation for the gradient at P. We want to work out the exact gradient. So remember what I said, we need to consider the point Q ever approaching the point P. So we need to imagine point Q is so close to point P that it actually is the point P. Now let's have a think about that for a moment. What must the value of h be when Q is the same as P? Well, h must be equal to 0 because this distance here must be 0 in order for point Q to be equal to point P. Now what problem do you think arises when we have h is 0? Yes, you've got it. We're dividing by h here, aren't we? And we cannot divide by 0 because otherwise we'll get an undefined answer. So we must think about something else. Instead of actually substituting h as 0, we need to consider the limit. What happens as h approaches 0? So in other words, what happens as h gets ever so small that it approaches 0? And for that, we need to introduce some notation, what we call limit notation. So what I'm going to do is I'm going to write f prime of x naught. So this is the notation we use for the derivative of a function. If the function, the original function, is f of x, we write the derivative of that function, in other words, the gradient function, f prime of x. In this case, we're dealing with x naught because that's my x coordinate in question. And that's equal to, so this time we need to take the limit as h tends to 0 of this function here. So f of x naught plus h minus f of x naught all over h. And this is the formula that we use to differentiate functions from first principles. And we're going to have a look at some examples. So let's have a look at an example question. Suppose we want to prove from first principles that the derivative of x squared is 2x. So when we're asked to prove from first principles the derivative of a function, the first thing that should come to mind is the formula, the limit definition of a derivative. Okay, so we've got our function f of x equals x squared. So let's apply the limit definition of a derivative. So what I'm going to start with is f prime of x because that's my notation for the derivative of a function. And then what I've got is I've got the limit as h tends to 0 of f of x naught plus h, or in this case f of x plus h. So f of x is x squared, So therefore, if I consider f of x plus h, what I'm doing is I'm just substituting x for x plus h. So what I get is x plus h squared, and then that's minus the original function f of x, which is x squared. So x squared, and that's divided by h. So what we can do now is we can expand the brackets that are on the top. So we've got the limit of h tending towards 0. Now you can check this yourselves, but I'm just going to do this quickly. Expanding x plus h squared, what I'm going to get is x squared plus 2hx plus h squared, and then I'm subtracting x squared. And that's all over h. Now notice, as if by magic, that the x squareds cancel, because what we've got is we've got x squared minus x squared, so we can cancel them out. And then what I'm left with is the limit as h tends to 0 of 2hx plus h squared on the top. And that's over h. Now what you should notice is that in the numerator we've got a common factor of h. So what I can do is I can factor out an h, because when I factor out the h, it can then cancel with the h that's on the bottom here. So let's do that. If I factor out an h on the top, what I'm going to get is h bracket 2x plus h. And then notice if you expand that, you get back to this 2hx plus x squared. And then that's over h. So as I mentioned, the reason I've done that is because notice I can cancel the h on the top with the h on the bottom. And that's the whole point actually. We actually want to get rid of the h on the bottom because we cannot divide by 0. Okay? So then what I have is the limit as h tends to 0 of 2x plus h. Okay, so what we can do now is, because we don't have h on the bottom, we can now substitute h for 0. So what this is going to become is 2x plus 0, and 2x plus 0 is of course just 2x. So that is the derivative, or the gradient function, of f of x equals x squared. So that's it for today. Before I leave, I'm just going to leave you with this question. Can you prove from first principles that the derivative of x cubed is 3x squared? So can you prove from first principles that the derivative of x cubed is 3x squared? Feel free to comment your answers in the comment box below. And also, if you could like and subscribe, it'll be much appreciated. And I look forward to seeing you in the next video when we have a look at how to work out the derivative of a function without having to worry about the limit definition of a derivative. So I shall see you in the next video. See you soon. Bye bye.